In this problem, we have a beam subjected to multiple distributed loads, and it is supported by a fixed support at point A. And we need to determine all the support reactions at the fixed support. So the first thing we want to do is to replace the distributed loads with concentrated forces. So for the first region, we have a uniform load. Therefore, the concentrated force is right here at the center. The location is going to be 0.9 meter from point A. And the magnitude will be 80 multiplied by 1.8, which equals to 144 Newton. For the second region, we have a linear distributed load. It varies from 80 Newton per meter at point D to 0 at point B. Because the shape looks like a triangle, the concentrated force is right here at the central location of the triangle, which is 1/3 of 1.8 meter from point D, which is 0.6 meter from point D. In other words, 1.8 plus 0.6 meter, which is 2.4 meter from point A. And the magnitude is 1/2, 80, 1.8, which is 72 Newton. It's basically calculating the area of the triangle. And next, we have another linearly distributed load. So again, the concentrated force is right here. 1/3 location from the base, therefore, is 0.4 meter from point C. And the magnitude is, again, the area of the triangle, 1/2 times 60 times 1.2, and that is 36 Newton. So after we have done this preparation work, we're ready to draw the free body diagram. So we have this L-shaped beam here. Okay, and we have 36 Newton force right here. We have right here the 144 Newton force, and right here the 72 Newton force. So these are the applied forces. And we have a fixed support at point A, which prevents translational motion in both x and y direction. Therefore, it exerts forces in both x and y directions. And also it prevents rotation. Therefore, it provides a couple moment support as well. So we have overall 3 support reactions, AX, AY, and then our moment, MA. As you can see, I always draw my unknown forces or reactions in their conventionally positive directions. So now we have completed this free body diagram. We have one rigid body free body diagram, 2-dimensional, 2D, from which we can write 3 equilibrium equations, and we do have 3 unknowns, AX, AY, and MA. So after we've done this analysis to count our unknowns and our equations, to make sure that we have enough equations to solve for our unknowns, now we move on to write our equations. So we have resultant force along the x direction, that equals to AX minus 36, and that is 0. Resultant force along the y direction equals to AY minus 144 minus 72 equals to 0. Resultant moment, again, we summarize the moment about point A because this way the unknowns AX and AY do not show up in our moment equation because they both have lines of action passing through point A, so they do not create moment about point A. So we still have our unknown free couple moment MA. So this MA right here is this one. It's one of the unknowns we need to solve for. And then the 144 Newton force creates clockwise rotation with a moment arm of 0.9 meter. And then the 72 Newton force also creates clockwise rotation with a moment arm of 2.4 meter. Lastly, the 36 Newton force creates counterclockwise rotation. The moment arm is this distance right here. This distance is 1.2 minus 0.4, therefore 0.8 meter. So now we have 3 equations and 3 unknowns. This is not difficult to solve because each of the three equations only contains one unknown, so we can solve ax from this one, ay from this one, and ma from this one. Therefore, ax equals to 36 Newton, ay equals to 216 Newton, and lastly, ma equals to 274 Newton meter.